last lecture we found that if F is any field, then any n dimensional vector space over F is isomorphic to F n, and therefore, we concluded that when we are talking about vector spaces over F, the main basic vector spaces are this F n. Now, in particular, if we take F to be the field of real numbers, then the basic vector space of dimension k is R k, and it is because of this reason that we study R k in great detail. So, hence we look at R k in more detail. The first thing that we observe is R k being a vector space, it already has this basic algebraic structure given by the two basic operations of the vector space, namely addition and scalar multiplication. Now, we are going to bring in more structure which is more geometric in nature on the space R k. So, we look at the notion of first the dot product, which most of you will be familiar with. Let us consider the vector space R 3. You may recall that if we take any vector x whose components are x 1, x 2, x 3 and a vector y whose components are y 1, y 2, y 3, then we define the dot product. This is in the vector calculus, vector algebra parlance known as the dot product x dot y. It is defined to be x 1 y 1 plus x 2 y 2 plus x 3 y 3. We now generalize this idea. So, we generalize, then we take R k for any k. Now, not k not necessarily 3, it may be 100, it may be 20, it may be 30, fix a k, then look at the k dimensional vector space R k, and if you take any two vectors x 1, x 2, x k and y equal to y 1, y 2, y k, analogous to the dot product, we now define the dot product in R k, and from now on we will refer to this as the inner product in R k, and instead of x dot y we will denote it by x comma y within a bracket. So, we define inner product of x with y as it is denoted by x comma y with a bracket, and it is defined to be x 1 y 1 plus x 2 y 2 and so on x k y k. You may notice that this is the same as taking the matrix y and taking its transpose and multiplying with the matrix x. The column matrix y, its transpose will be a row matrix. So, we have a row matrix and we multiply this row matrix by this column matrix, the result will be a number, and therefore, you observe that the inner product of two vectors is a number. Okay. So, we define the inner product of two vectors in R k by this definition. We observe first some simple properties of this inner product. From the definition, we observe that x comma x will be x 1 squared plus x 2 squared plus x 3 squared plus x k squared. So, we will simply write it as j equal to 1 to k x j squared, and therefore, this being the sum of non-negative quantities, this will be always greater than or equal to 0, and when will that become 0? When the sum of the squares is 0, but the sum of the squares is 0, since all are real numbers, is only when each one of these entries is 0. That means, x j is 0 for all j, but x j is 0 for all j means x is equal to 0. So, if and only if x is the 0 vector. So, the first important property is the inner product of any vector with itself is always non-negative, and it becomes 0 only when the vector is the 0 vector. The second important property is we have a product. Note that the product of two vectors, this product, this inner product, the result is not a vector, but is a number, is a real number, and this real number is always non-negative and becomes 0 only when x is the 0 vector. Now, we have introduced some new action in the vector space. The moment we introduce some new action, we are interested in what are its implications on the two basic operations of the vector space, namely addition and scalar multiplication. Before that, we observe that the definition here is symmetric in x and y. If we interchange the positions of x and y, the result is going to be the same. We will get y 1 x 1, y 2 x 2, y n x n, but the result is going to be the same. Therefore, we observe the first this symmetric property x comma y is the same as y comma x for every x y in R k. That is, the inner product of x with y is the same as the inner product of y with x. Then we look at the effect of this operation of inner product with the two basic algebraic operations in the vector space, namely addition and scalar multiplication. So, suppose I take two vectors x and y and add them and then take the inner product with z, that is the same as, by definition, j equal to 1 to k, x plus j has coordinates x j plus y j and z has coordinates z j, which is equal to j equal to 1 to k x j z j plus j equal to 1 to k y j z j. But this first sum is nothing but the inner product of x with z plus the second term is the inner product of y with z, which simply boils down to saying that this inner product is distributive from the right. X plus y comma z is x comma z y comma z. So, we will say inner product is right distributive. This is the effect of addition with interpreted with respect to the inner product. Next, we will see the effect of this inner product on scalar multiplication. This is true for any vectors x, y, z and R k. Next, we look at the effect of inner product on scalar multiplication. So, we take a vector x and we take a scalar alpha and then take its inner product with a vector y. What is this equal to? The components of alpha x are alpha x j and this is to be multiplied with the components of y j, and this is the same as summation j equal to 1 to k, alpha can be pulled out of the summation x j y j, and the summation is nothing but x comma y. So, it is just alpha x comma y. This simply says that the alpha can be pulled out of the inner product from any one of these factors, from the first factor. Remark, since the inner product is symmetric, right distributive will also imply left distributive, and pulling out alpha from the first term in the inner product will also imply pulling out alpha from the second term in the inner product. So, using the symmetry property which we have called as 2, this symmetry property, using 2 in the distributive property and the scalar multiplication property, we get x comma y plus z is equal to x comma y plus x comma z for every x y z in R k, that is left distributive. The inner product is left distributive, and we get x comma alpha y is the same as alpha into x comma y for every alpha in f and x in R k. Here also we have to say that for every alpha in f, x y in R k. So, we have left distributive, right distributive, and the constants can be pulled out of the inner product either from the first factor or from the second factor. So, this is a very important generalization of the notion of the dot product that we had in vector algebra. What does this inner product give us? So, the effect of inner product. If you recall, again look at R 3. Now, for x comma y in R 3, which is the dot product, now we are going to denote by this notation, is summation j equal to 1 to 3 x j y j. And we now, if we now take x comma x, we get j equal to 1 to 3 x j squared, which is the Euclidean length of the vector in the 3 dimensional space, the square. So, the square of the Euclidean length, which we normally define as the length, that is the distance from the origin to the point x 1, x 2, x 3. And therefore, we have that the length, which we will now denote by this, the length of x is square root of x comma x. Now, this is generalized to define the length of a vector from the inner product through this definition. So, moment we have the notion of the inner product, we can define the notion of the length through this definition by the experience that we gain from looking at R 3. So, therefore, generalize in R k for any x belonging to R k, we define the length of x, which we denote by this symbol, and from now on call it as norm of x, as norm of x by definition is square root of x comma x. Notice that there is no problem of taking the square root of x comma x, because we have already observed that for any vector x comma x is a non-negative quantity, and therefore, we are taking a square root of a non-negative quantity. So, we will get only a real quantity. However, you may wonder, there are two square roots plus and minus, which one do I take? Since we want the length to be non-negative, we do not want negative lengths, therefore, we always take that square root which is not negative. Okay. Now, what are the properties of this length? This way of defining the length, since we have generalized from R 3, the properties of the length in R 3 are carried over to the properties of the length in R k. What are these properties in R 3? If you take 3 dimensions and if you take any vector, the length is always going to be non-negative, and only time the length is 0 will be the 0 when the vector is the 0 vector. Secondly, what is the effect of the length on the two basic operations of these vectors? If we multiply a vector in 3 dimensions by a number, if the number is positive, the length simply gets multiplied by that number. If the number is negative, the length simply gets multiplied by the modulus of that number. So, in any case, the length gets multiplied by the modulus of the scalar, which is multiplying the vector. And we have a simple law in geometry, that if we have a triangle, any side, its length must be less than or equal to the sum of the two sides. In vector language, this translates into what is known as the triangle inequality, that the length of the sum of a vector is less than or equal to the sum of the lengths of the vector. Let us summarize this. These get generalized in the most general setup of R k as well. The first property is the length of a vector is always non-negative, because square root of x comma x is always non-negative, and equal to 0 if and only if this is 0, the square root is 0 if and only what is inside, that x comma x is 0, but the property of the inner product says x comma x is 0 only when x is 0, and therefore, we get this is equal to 0 if and only if x is the 0 vector. And when you multiply a vector by a scalar alpha, this is for every x in R k, when you multiply a vector by a scalar, then the length gets multiplied by the absolute value. So, for every alpha in f and for every x in R k. And the third is the property of this effect of this notion of length on the basic operations of addition. X plus y is less than or equal to x plus y, the length of x plus the norm of x plus the norm of y for every x y in R k. This is called the triangle inequality. We shall not get involved in a proof of this. This follows from what is known as the Cauchy-Schwarz inequality. We shall look at it at a later time, but it follows from the notion of a Cauchy-Schwarz inequality. So, in other words, we have on R k we have the inner product. The inner product in turn induces the notion of a length or the norm, and this obeys all the standard ideas that we have about length, that length should be non-negative, it should become 0 only when the vector is 0, and length should get dilated by the absolute value of the scalar multiplying it, and the triangle inequality is satisfied. There is one more effect of the idea of inner product, which is the notion of orthogonality. This is where the inner product brings in the orthogonal geometry. So, we should now look at the next implication of the inner product. The first implication of the inner product is that induces the notion of a length. the second interpretation or the second influence of the inner product is the notion of the orthogonality. So, what do we mean by that? Again look at R 3. So, in R 3 in our vector calculus or vector algebra course, we learned that if x and y are in R 3, we say x is perpendicular to y, or we have x is perpendicular to y if x dot y is equal to 0, which x dot y is what we have generalized as x comma y, that inner product. So, we generalize this notion to say that in R k x is said to be orthogonal to y if the inner product of x with y is 0. So, we generalize this idea to the following: if x y belong to R k, we say x is orthogonal to y if x comma y equals, if and only if x comma y equal to 0. No, recall that the inner product of two vectors is a number, that number must become 0. If the inner product of two vectors is 0, we say x is orthogonal to 0. Now, if x y is 0, y x is also 0. So, if x is orthogonal to y, y is automatically orthogonal to 0. So, x y equal to 0 if and only if y x equal to 0. Hence, x is orthogonal to y if and only if y is orthogonal to x, and that is why we will not say x is orthogonal to y, y is orthogonal to x, we will simply say x and y are orthogonal. Okay. So, now note x comma theta k for any x in R k. What is x comma theta k? We have to look at j equal to 1 to k x j and the jth component of theta k multiplying. Now, but the jth component of theta k is all 0 and therefore, that is 0. So, that implies theta k is orthogonal to all the vectors in R k. Now, in fact, this is a characterization of the 0 vector, because this is the only vector which is all orthogonal to all the vectors. In fact, theta k, the 0 vector theta k is the only vector orthogonal to all the vectors in R k. This is the only vector, no other vector can be orthogonal. Why? Suppose x is in R k and x is orthogonal to all vectors. If x is orthogonal to all vectors, this implies x is orthogonal to itself, because it is orthogonal to all the vectors. In particular, it must be orthogonal to itself, but if x is orthogonal to itself, the inner product of x with itself must be 0, but we know that the inner product of a vector with itself is 0 only when x is equal to theta k. Therefore, the only vector which is orthogonal to all the vectors is the 0 vector. Let us look at some simple examples of this orthogonality. Let us consider R 4. Consider the vector x equal to 1, 1, 1, 1 and y equal to 1, minus 1, 1, minus 1. Clearly, we have x comma y is x 1 y 1 which is 1, x 2 y 2 which is minus 1, x 3 y 3 which is 1, x 4 minus 4 x 4 y 4 which is minus 1. So, it is going to be 1 minus 1 plus 1 minus 1 which is 0, which implies x is orthogonal to y in the vector space R 4. Let us look at another example. Let us look at R 3 and let us look at x 1 or let us use a standard symbol. Let us call it as E 1 which is 1 0 0 and E 2 which is 0 1 0, E 3 0 0 1. Then clearly E 1 is orthogonal to E 2, E 1 is orthogonal to E 3, E 3 is orthogonal to E 2 because all the inner products are 0. Let us look at another simple example. Consider R 4, consider the vector x equal to 1 1 1 1. Now, let us find all those vectors which are perpendicular to x. So, let us find all vectors in R 4 which are orthogonal to x. So, now let us take a vector say u which is u 1, u 2, u 3, u 4. Suppose u is orthogonal to y x. This can happen only when the inner product of x and u is 0. But what is the inner product of x and u? It is u 1 plus u 2 plus u 3 plus u 4. So, this happens if and only if u 1 plus u 2 plus u 3 plus u 4 equal to 0. So, therefore, a vector is orthogonal to x if and only if the sum of all its components is equal to 0. That means, u must be of the form alpha, beta, gamma. Since the sum of the 4 components must be 0, the fourth components must be alpha minus beta, and thus where alpha, beta, gamma are real numbers. So, this is the set of all vectors which are orthogonal to x. Hence, the set of vectors of the form, I will call it u since I called there u equal to alpha, beta, gamma minus alpha minus beta minus gamma, where alpha, beta, gamma are real numbers. This collection of vectors is the set of all the vectors orthogonal to x. Let us now pursue this idea not just to finding the vectors which are all perpendicular to given vector x, but let us try to find the set of all vectors perpendicular to given set of vectors instead of just one vectors. So, what we now do is generalize this example. How do you generalize this example? The way we generalize this example is, let S be any non-empty subset of R k. In the above example, we have taken the set S to be this single vector x. We have just taken the S to be the single vector. now what we are going to do is take an arbitrary non-empty subset of R k and then we denote by S perp with a superscript perp the set of all vectors in R k which are orthogonal to all the vectors in S. So, therefore, in symbolically we can write S perp is the set of all the vectors u in R k such that u must be orthogonal to every vector S. So, we must have S comma u must be equal to 0 because u must be orthogonal to S, and this must happen for every S because it must be orthogonal to all the vectors. So, it is the set of all u in R k such that S comma u is 0 for every S in S. This is the collection of all the vectors which are perpendicular to every one of the vectors in S. Now, is this an empty collection or a non-empty collection? Will there be any vector at all which is perpendicular to all the vectors in S? We know that the 0 vector is perpendicular to all the vectors in R k, and hence in particular the 0 vector is perpendicular to all the vectors in S. So, okay, clearly theta k belongs to S perp since theta k is orthogonal to all vectors in R k, and hence in particular to all vectors in S. So, the 0 vector belongs to S perp. Since S perp is now a non-empty subset of R k, the moment we have a non-empty subset of R k, we wonder whether it will be a subspace. So, now since S perp is a non-empty subset of R k, we check if it is a subspace of R k. Now, it will be a subspace of R k. Remember, any subset of R k will be a subspace of R k if it is non-empty, which is given, then it is closed with respect to the two basic operations of addition and scalar multiplication. So, for this we have to check if x and y belong to S perp, imply x plus y belong to S perp, and that is closure with respect to addition. 2, if x belongs to S perp, alpha is any real number, whether this implies alpha x belongs to S perp. So, we have to check whether S perp is closed with respect to addition and closed with respect to scalar multiplication. So, let us look at one. We are given x y in S perp. What does that mean? X is in S perp, which means x is orthogonal to all the vectors in S. That means S x is equal to 0 for every S in S. Similarly, y is in S perp. So, S y is equal to 0 for every S in S. So, S x must be equal to 0 for every S in S, S y must be equal to 0 for every S in S. Now, if we add, we get S x plus S y is 0 plus 0. So, it is 0 for every S in S. Now, we know that the inner product is right distributive and left distributive. So, we can write this as S of x plus y is 0, because S of x plus y, S comma x plus y is S comma x plus S comma y. So, this is for every. This says the vector x plus y is orthogonal to all vectors in S. That is exactly the meaning of the fact that x plus y belongs to S perp. Therefore, we have seen that whenever x and y belong to S perp, x plus y also belongs to S perp. This shows that S perp is closed under addition. So, hence S perp is closed under addition. 2, we have to now check whether it is closed under scalar multiplication. So, we are given x in S perp, alpha a real number. What does that imply? X in S perp again says x must be orthogonal to all the vectors in S and alpha is in R. Now, S comma x is a real number, alpha is a real number. So, we can multiply, and on the right hand side we get alpha into 0 is 0. Now, we know that a constant can be pulled in and out of an inner product from any one of the factors. So, this is the same as S of alpha x equal to 0 for every S in S. This is the same thing as saying that alpha x is orthogonal to all vectors in S. That is the same thing as saying alpha x belongs to S perp, and hence S perp is closed under scalar multiplication. So, what we have seen is that the S perp is a non-empty subset, of R k, which is closed under addition and scalar multiplication. This means that S perp is a subspace of R k. So, what we have done is we have started with an arbitrary non-empty subset S, and we have concluded S perp, the collection of all vectors which are perpendicular to all the vectors in S, must be a subspace. Note that we have not assumed that the original set S was a subspace. Irrespective of whether the original set is a subspace or not, the perp S perp will always be a subspace. Okay, so note, we have not assumed S to be a subspace, but still S perp is a subspace. So, the conclusion is the S perp for any non-empty subset S in R k is always a subspace of R k, irrespective of whether S is a subspace or not. So, whether S is a subspace or not, S perp is always a subspace. Of course, in particular, if W is a subspace of R k, then W perp will also be a subspace. We shall be looking at such perps of subspaces when we analyze a matrix. Let us look at one or two simple examples. Let us consider V to be R 3. So, in other words, we look at the subspace, the vector space R 3, we look at the vector space R 3 and let us take the set S consisting of two vectors, where u 1 is 1 1 1 and u 2 is equal to 1 2 3. Notice that S is not a subspace, because the vector 1 1 1 is there, but multiples of this vector are not there. So, here note S is not a subspace. No, S is not a subspace. Now, let us find S perp. In this case. Now, what is S perp? S perp is the collection of all the vectors which are perpendicular to all the vectors in S. So, suppose a vector x belongs to S perp, that implies and implied by this can happen if and only if x is orthogonal to u 1 and u 2, because a vector gets qualified to be in S perp only when it is orthogonal to every one of the vectors in S. That is, if and only if its inner product with u 1 must be 0 and its inner product with u 2 must be 0. Now, if x is x 1, x 2, x 3, the inner product with u 1 will give me x 1 plus x 2 plus x 3 as 0, and its inner product with u 2 will give x 1 plus 2 x 2 plus 3 x 3. Let us now call this equation as 1 and call this equation as 2. So, x 1, x 2, x 3 must be such that both these equations are satisfied. Therefore, a vector x qualifies to be in S perp if and only if its components x 1, x 2, x 3 satisfy these conditions. Now, there are two equations for these three coordinates, and therefore, we can eliminate two of these variables. So, what does this tell? If we now subtract the first equation from the second equation, gives x 2 plus 2 x 3, x 2 plus 2 x 3 is 0, or x 2 is equal to minus 2 x 3. If we now use this in 1, we get x 1 minus 2 x 3 plus x 3 as 0, which gives x 1 equal to x 3. So, we have to have x 1 to be equal to x 3, x 2 to be minus 2 x 3, and x 3 can be chosen arbitrarily. So, if and only if x is of the form x is equal to, if we choose x 3 as alpha, x 1 has to be chosen as alpha and x 2 has to be chosen as alpha minus 2 alpha, and therefore, we get S perp consists of all these vectors which are of this form where alpha belongs, and this is clearly a subspace and that can be easily verified. So, for this collection of vectors S which we found, which had here this set of vectors, the corresponding S perp is given by this subspace of vectors. The S perp is always a subspace. Now, let us consider a subspace W in R 3, W subspace of R 4, where W is defined to be the collection of all vectors of the form alpha beta, alpha plus beta, alpha minus beta, alpha beta belonging to. Now, what is W perp then in this case? Now, let us say that we want to find x belonging to W perp. Now, what does it mean to say that x is perpendicular to all the vectors in W? Now, suppose x is perpendicular to the basis vectors in W, then it will be automatically perpendicular to all the vectors in W. Let us verify this. Okay. Now, a basis for W is u1 equal to 1 1 1 1 0 1 1. This is taken by, this is got by taking alpha equal to 1 and beta equal to 0, and now taking alpha equal to 0, beta equal to 1, we get these two vectors are linearly independent, are in W, and any vector is of the form alpha u1 plus beta u2. So, therefore, these form a basis. Now, any vector in W is of the form alpha u1 plus alpha u2. Alpha u1 plus beta u2. Now, suppose x is perpendicular to u1, that is, suppose x is orthogonal to u1 and u2, then x comma u1 equal to 0, x comma u2 equal to 0, and that implies x comma alpha u1 is 0, x comma alpha u2 is 0, because we can pull out constants in and out. We can take a different constant here, beta if you want, and then that will say, if we add both of them, x of alpha u1 plus x of beta u2 equal to 0, and using the distributivity we get alpha u1 plus beta u2 equal to 0, which means x is orthogonal to all vectors in W. And therefore, to check whether a vector is orthogonal to all the vectors in W, is enough if it is check whether it is orthogonal to the basis vectors. So, x belongs to W perp if and only if x is orthogonal to u1 and u2. If and only if the orthogonality with u1 will means x1 plus 0 times x2 plus x3 plus x4 is equal to 0. So, therefore, if and only if x1 plus x3 plus x4 is equal to 0. Now, the orthogonality with x2 will give me x2 plus x3 minus x4 is equal to 0. So, x2 plus x3 minus x4 is equal to 0. Now, the first equation gives me x1 equal to minus x3 minus x4, second equation gives me x2 equal to minus x3 plus x4. So, it says x3 and x4 can be chosen arbitrarily, then x1 x2 has to be chosen like this. So, we get W perp is equal to the set of all vectors of the form u equal to, if we choose x 3 as alpha, x 4 as beta, then x 2 has to be chosen as minus alpha plus beta and x 3 as minus alpha minus beta, where alpha beta belong to R. And now it is easy to verify that this is a subspace of R k. Now, what is the basis? W perp being a subspace, a basis for W perp is given by V 1 equal, if we take alpha equal to 1 and beta equal to 0, we get minus 1 1 1 0, and V 2 by taking alpha equal to 0 and beta equal to 1. So, this forms a basis for W perp. So, the dimension of W perp in this case is 2. So, we have this notion of the perp of any arbitrary set, and the perp of any arbitrary set is automatically a subspace of R k, and in particular the perp of a subspace is always a subspace. Now, we would like to generalize the notion of I j k vectors, which leads us to the notion of orthonormal sets. So, if you now look at the R 3 space, then take the vectors I, which we in vector space we denote by I, whose components are 1 0 0, and the vector j, which we denote by 0 1 0, and the vector k, which we denote by 0 0 1. These vectors have the property, any two distinct vectors in this collection are orthogonal, and every vector has length 1. When we generalize this notion, we get the notion of an orthonormal set in a R k. So, we have in R k a set S equal to u 1, u 2, u k vectors. So, if you take a set of vectors in R k is said to be orthonormal set if you take u I comma u j, the inner product between any two vectors, this must be equal to 0 if I not equal to j, 1 if I equal to j. Now, what does the first condition say? The first condition says I not equal to j, that means they are distinct vectors, then the inner product is 0 means they are orthogonal. So, distinct vectors, any two distinct vectors in S are orthogonal. The second condition says if we take a vector and inner product with itself, we get the square of the norm, the norm is 1. The second condition says that any vector in S has length 1. Our idea is to use this generalization of the I j k vectors to similarly generate a orthonormal basis analogous to the I j k basis for the R 3 to a general R k, and use this construction of orthonormal basis to analyze our problem on the matrices. In the next lecture, we will look at the important notion of an orthonormal basis.